Hello, Honors Physics students. Alright, let's go ahead and get started with our problem set with number 21. Go ahead and read problem 21. It's a real simple one. Pause the video, solve it, come back. Okay, super simple here, starting off with drawing a schematic. So here's my schematic. If yours doesn't look exactly like this, it's fine, but look, it's just one source of voltage and one resistor. Doesn't really matter how you orient it, there's nothing else to do here. I like to label it right there on the diagram. I'd suggest you do as well. So there's the 12-volt battery, there's the 6-ohm resistor. You don't necessarily have to put all the decimal points and sig figs and stuff like that, or just sort of sketching at the diagram. Okay, then it couldn't be any easier here. We want to find the currents. Now, of course, you're using Ohm's law, I equals delta V over R. Here, though, I'm putting the subscripts, and to be quite honest, if there's only one resistor here and one source of voltage, there's nothing really interesting or different or weird or difficult going on. So if you didn't put the subscripts here, okay, but you'll soon see the subscripts that I'm using are going to be very, very important. So if you want to put it here, okay, but for this problem, if you didn't, not the end of the world. Okay, so it's 12 volts for 6 ohms, simple, it's 2 amps. And then, what's a really good idea is to label this on the diagram. I'm always a big fan of doing that, and so as we start doing more and more of these problems, I'm going to ask you to draw your diagrams nice and large. This is a pretty small diagram anyway, so it's not really not a whole lot of detail that needs to be on it, but here's where we like to put 2 amps. This is the current going through the battery. All the charges go through the battery, so we label the 2 amps that are coming out of the battery, and of course, remember the long line, of course, represents the positive terminal, and we're tracking conventional current, the flow of positive charge. The protons are held against their will by the positive terminal. They come out of that end, and of course, really they're going all the way around, but I just like to label it there. It's the easiest way to think about it. But of course, all those charges are going to go through the 6 ohm resistor, so this is also the current through the 6 ohm resistor, which here I'm labeling as I6, the current through the 6 ohm resistor. Okay, because and then I like to put it right here on the diagram so you can see all the charges come out of the battery, they all go through the 6 ohm resistor, round and round they go. Great. Alright, want to find the power generated by the battery, so I'm going to call that P total. Now again, if you didn't call it P total, it's okay, there's only one thing going on here, but it is important that we start linking all the subscripts. If we are finding the total power, that's linked with the total current and the battery voltage, which is just these numbers multiplied, nothing difficult, so of course it'll be 24 watts. And since any charge that gains 12 volts to the battery would have to lose 12 volts by going through the resistor, we could say it's also the power dissipated by the resistor. This is the language we use. This is the power generated by the battery, this is the power dissipated by the resistor. Why is it 12 volts here? Well, we go to our ski resort analogy. Here's the bottom of the mountain, the negative terminal. That's where the skier gets on the ski lift. Is brought to the top of the mountain, gaining 1,200 meters of height. Right here, the charge gains 12 volts. And then, the only place to pick up the ski lift is again back there. To go back there, they have to go through the resistor, which is coming down the mountain, and the voltage drop. So if they went up 1,200 meters, they got to come down 1,200 meters. They go up 12 volts, got to lose 12 volts. And so, of course, the voltage gain has to be the voltage loss. All right. So everything's really, really simple. Nothing difficult here whatsoever. Fantastic. Let's go on to problem 22. All right, so I'm going to lead you through this one. Go ahead and read it, and then we'll do it together. Okay, so the first part is just drawing the schematic. So this time, definitely, pause the video, draw your own schematic, because I don't want to influence you. I want to see what you do. I'd like to see what you do if we're in class together, but then you'll see mine. Okay, so I'm going to show you my schematic, but if yours looks a little bit different, it's okay as long as you follow the rules for them being in series. So I specifically try to draw my schematic for them in series, very much similar to the one I did in problem 21, where there's the 12-volt battery, here's the 6 ohm resistor, and then just adding the 2 ohm resistor in series so we can make comparisons. Now, if you didn't do that, that's fine. In fact, you don't have to go back, you don't have to change your diagram, you just have to make sure your diagram is nice and big. I did say that in the previous problem, because we are going to start labeling a whole lot more information on the circuit, and if it's all very, very small, it's going to be crowded, you won't be able to see what's going on, and then what's the point of labeling it, okay? But definitely they have to be in series. We know they're in series because there's only one path, and any charge that goes to the 6 ohm resistor has to go through the 2 ohm resistor. As long as you have that sort of connection with one path, they're in series, it's great. Alright, finding REQ is not difficult. I mean, yes, you should show your work. I'm not showing all the equations here just for simplicity of seeing it on the screen, but we're just adding them together. It's 8 ohms, fantastic. Yes, we deal with sig figs here, whereas we don't necessarily put sig figs on the diagram, just for ease of use. Okay, we want to find the total current. Okay, so now is the time where you have to be using your subscript. So if you just wrote I equals delta V over R, at this point, you must change it. I require that you change it because we are finding the total current. That's the current going through the battery, which means we must be using the battery voltage and the equivalent resistance. Total current goes with total voltage, goes with total resistance. As the problems get more and more complicated, these subscripts will be your saving grace, so you don't get confused. 2 resistors is not that complicated, and so maybe you'll be okay with it, but when it gets much more complicated, these subscripts are what links everything together. And so I require that you do it this way. So battery voltage is 12 volts, REQ is 8 ohms, it's very simple math here, we're going to get 1.5 amps. And then, just like I did before, you're going to label it on the diagram. Again, this is the total current, so it's labeled as coming out of the battery. So I draw the 1.5 amps here coming out of the battery. Our next part is the power. We want to find the power generated by the battery. And so, again, we want to find P total. Now, we have 3 different power equations. There's no particular reason to do one or the other, but I'm going to first do I delta V. So go ahead and write the equation with I delta V, but I want you to write all the correct subscripts. So it should look like this. Oh, I forgot. I'm sorry. We used I delta V before. I wanted to use I squared R. Oh, I messed up. All right, so I squared R. I apologize. Okay, so P total is going to go with I total squared and REQ. If it was P total is I delta V, it would be I total delta VB. I just wanted to get the other equations in here so we can see what that would look like. So we're again using total current at total resistance. No matter how you do it though, you're going to get 18 watts. So try with the other equation, try with this equation. No matter what, we're going to be getting 18 watts, no problem there. All right, now we're going to go on to the individual resistors. We're going to find their current, their voltage drop. That's the language I introduced before, right? The voltage across the resistor is a voltage drop, and the power. So at this point, I do want you to pause the video and try to find all these terms on your own, and then come back to see how I do it. Okay, so what we want to do is remind ourselves we have this chart that lists the differences between series and parallel. So if you don't have it yet, have it in front of you. But I will have it up here, a little recreation of it, the important stuff here. We are in series, we're only on this side of the chart, and we see what could we find without doing any calculations. Well, you should see that the currents are the same in series. So without doing any calculations, we know the two currents are going to be 1.5 and 1.5. Now notice here I'm labeling this as I6 and I2 because I could label it I1 and I2, calling these R1 and R2, but I never really know what order you're going to put them in. So I don't want to call them necessarily 1 and 2. Here I'm labeling everything by what resistance it's linked to. So this is I6, that's the current through the 6 ohm resistor. I2 is the current through the 2 ohm resistor, and the currents have to be the same, and now we draw them on the diagram. So here's 1.5 amps coming out of the battery, 1.5 amps going through the 6 ohm, 1.5 amps going through the 2 ohm. There's only one path. There's no other places for the charge to go. The currents must be the same. They have to be. What about the voltages? Well, the voltage, that splits, so the voltages are not going to be the same. So how do we find the individual voltage drops? We're going to use Ohm's law. So for delta V6, we're going to write this as I6R6. Again, if you just write delta V equals IR, it's okay. I'm sure you're going to get the right answers, but you do it this way so you know exactly what you're doing. And when you label it on the diagram, everything is linked here together. There's the current of the 6 ohm. Here's its resistance. Put them together, you get 9 volts. Easy, easy, easy. By the same token, for delta V2, it's going to be I2R2, right? Makes perfect sense. Again, you've labeled it on your diagram, so they're right next to each other. You can do the math in your head. It's going to be 3 volts, and then you label it on your diagram. This is why I ask that you draw a large diagram, because now we're going to draw the voltage drops right here on the diagram, linking this voltage drop to the 6 ohm, this voltage drop to the 2 ohm, so we can see it, and now we can see, does it make sense? How do we know if these voltages are making sense? Well, we know that the sum of the gains has to be the sum of the drops. So we watch an individual charge. A charge starts here at the bottom of the mountain at the negative terminal, goes through the ski lift to the top of the mountain, gains 12 volts. The only way this skier can come all the way down the mountain is by losing all 12 volts, because it goes up 12, it's got to come down 12. So it goes through the first one and loses 9 volts. Has it lost all 12? No, it doesn't make any sense, right? It loses the rest of its 3 volts. It lost a total of 12 volts. This makes sense. These drops have to add up to the original gain, so we know things are making sense. All right, now for the power ones, well, we've already done I delta V, we've done I squared R. Let's do delta V squared over R. So I want you to write that equation for power 6 with the appropriate subscripts. Okay, so it should look like this, delta V6 squared over R6, right? Everything, all the 6's are together. And now we just do the math, and we get 13.5 watts. And of course, you can pick any of the power equations. You didn't have to do it this way, but I just chose this one so we could see the different variations. For P2, here I'm going to do I squared R. Doesn't really matter which you do. Pick your favorite one. Try it out on your own. You should be getting 4.5 watts. But again, I just want to show all the subscripts linked together. Fantastic. All right, let's go on to problem 23. So I want you to do all problem 23 completely on your own, then come back to the video to see how I did it. The first job is to draw the schematic. So I'm trying to make these comparisons among these circuits in 21, 22, and 23. So I'm drawing the circuit in 23 very similar to the one I drew in problem 21, just adding the extra resistor in parallel. So this is what my diagram looks like. Now, again, if yours doesn't look like this, it's fine. You don't have to redo anything. I just like to do this so we can see comparisons. As long as these two are in their own independent branch, we have this part of the circuit called the junction, right, where the wires join together. They split apart here, they join back together over there. You have them in parallel. as long as you do this. Okay, so we first want to find REQ, so now they're in parallel, so you can do your 1 over business, or, since there's only 2 of them, we can do our shortcut. I wonder how many of you did that, right? The shortcut, product over the sum. We can do this in our head. The product is 6 times 2 is 12. The sum is 6 plus 8 is 6 plus 2 is 8. 12 over 8, maybe you can do that in head, maybe you can't, but we should be getting 1.5 ohms. That's really not complicated. For the total current, we're doing delta VB over REQ, and again, hopefully you're starting to write the subscripts just like I've been telling you to do. We're going to get 8 amps, and then we immediately put it on our diagram. This is how we do circuits. We label everything on our diagram. For the total power, you can choose any of the ones you want. Here's the one I chose. I chose delta V over R, but I'm doing total power, so I'm doing the entire voltage, that's delta VB, and the entire resistance, that's REQ, not any individuals, right? And we should be getting 96 watts no matter how you did the power. I set up what I'm going to find for the individual resistors, and then I look at the chart, because I want to see what can I get here without doing any calculations. So the chart reminds us that in parallel, the voltages are the same. So without doing any calculations, we know the voltage drops will have to be 12 volts. They have to be, right? Any charge that gains 12 volts and comes back to the battery has to have lost 12 volts there, or a different charge getting 12 volts will have to lose 12 volts there. In parallel, the voltages are the same. Now, these voltages only happen to match the battery voltage because there's only one resistor on each path. If there had been more than one resistor, then other things would happen. But for this particular case, where it's nice and easy, just watch one charge gain 12, lose 12, gain 12, lose 12, back to start, the voltages are the same. The currents, however, have to split up. So when the 8 amps gets here, some will go this way, some will go the other way. How do we know? Well, we're not guessing here. We do it by equations. I mean, yes, you can do it by proportions also. There are ways of doing it, but I like to just go with the equation with Ohm's law. So for I6, it's delta V6 over R6. I hope you're doing what I'm doing by putting the subscripts there. And look, the way I've drawn it on the diagram, it's set up to do this. You don't have to do it this way, but I write the voltage over the resistance just like it is in the equation, just to help us out. It's a very visual way of seeing it. We know that's going to be 2 amps. 12 volts for 2 ohms is going to be 6 amps. Easy, easy. And then put it on the diagram. Here's the 2 amps going this way, the 6 amps going this way. Now, how do we check to make sure it works? Well, there's a couple ways. One is we know that the charges tend to take the path of least resistance. So when 8 amps get here to the junction, here's the path of large resistance, here's the path of small resistance, black diamond, bunny slope. We know that more charges will take the path of least resistance. So we got a 6 amps here, 2 amps there, that's good. But how do we specifically know it's working? Well, if 8 amps splits up, it better split up into 2 and 6. Right? Or at least they have to sum back together to make 8. Imagine it with skiers. Let's say a group of 8 skiers takes the trip to the top of the mountain, get to this part here, and 2 of them go this way, 6 of them go this way. So if 8 skiers go to the top of the mountain, a total of 8 skiers come down the mountain. This is working perfectly. We know things are working well. Okay, so now for the power, you can pick your favorite power equations. For example, if you did delta V squared over R, I'm just linking it with the subscripts here. For the 6 ohm resistor, which is getting 24 watts. For the 2 ohm, here I did it with I squared R. You should be getting 72 watts. No matter which equation you choose, you should be getting these values, 24 watts and 72 watts. Okay, now let's go back to problem 22. Go back to 22. Let's get rid of all this information. Let's say you got a little confused and you said, okay, so I know they're in series, and I think in series the voltages are the same. So let's say, for example, you immediately did this. Let's see how we know it doesn't make sense. We go back to our ski resort analogy, right? So here's a skier at the bottom of the mountain at the negative terminal, takes the ski up to the top, gains 12 volts, goes up 1,200 meters, right? And then the skier comes this way through the resistor, which means they're going down the mountain. They just lost 12 volts, lost 1,200 meters, right? And they go through this other resistor and again lose 12 volts, down another 1,200 meters, right? So in terms of voltage, this skier gained 12 volts. How much did this skier lose by coming down the mountain? Where is this skier, right? If he gained 12 and lose 24, that skier's underground. That doesn't make any sense. And that's the whole point. The ski resort analogy helps you visualize. If you make this assumption, how that doesn't make any sense, you know you did something wrong. We know that the gain of 12 volts has to match the total drop by going through both these resistors. That's the only way to get back to the bottom. Gain 12, lose a total of 12. Let's go to problem 23 and do a similar thing. Let's give it all this information. Let's say you got confused. You say, oh, they're in parallel. The currents have to be the same. If there's a total of 8 amps here, there's 8 amps here and 8 amps here. Now we go to our ski resort analogy. 8 amps, remember, that's current. That's the charges. That's the things moving. So let's say 8 skiers go to the top of the mountain, 8 skiers come down this, and at the exact same time, 8 skiers come down this trail as well. How many skiers just came down the mountain? How many went up the mountain? Right? If 8 skiers go to the top mountain and 16 come down the mountain, that doesn't make any sense. And that's the whole point. The ski resort analogy helps you find mistakes in your reasoning.